Okay, so today we're going to talk about principles for understanding bonding. So these principles are as follows. An atom is the most stable when its outer energy level is full of electrons. Atoms can attain full outer energy levels by gaining electrons, by losing electrons, or by sharing electrons with other atoms. If an atom gains electrons, it becomes negatively charged. If it loses electrons, it becomes positively charged. Negatively charged particles and positively charged particles attract each other, and similarly charged particles repel each other. These principles will be used to sketch atomic structure in a variety of substances. Once you have sketched the diagrams of the atomic structures of rock salt, a piece of plastic, and a piece of metal, you will be better able to explain the properties of these different materials. Sketching the atomic structure of substances containing more than one atom has 4 basic steps. Step 1. You need to draw the Lewis dot diagram of each atom that makes up the substance. Step 2. You need to determine which atom needs the most electrons to fill its outer level, and draw the Lewis dot diagram for this atom in the center of your diagram. Step 3, you need to connect the atoms in a way so that each atom's outer energy level is filled. And then examine the finished diagram. Step 4, you need to make sure each atom has a completely filled outer energy level. If it doesn't, you need to repeat step 3. Here are some examples of hydrogen, carbon, water, ethylene, and acetylene here, and their subsequent Lewis dot diagrams, and then the bonds that have been replaced. So these 2 electrons here are now replaced with this line here. So metals. Aluminum is a metal. This means that aluminum has luster and good heat and electrical conductivity. It also means that aluminum is malleable, which means it can be hammered into different shapes without crumbling, and ductile, meaning that it can be stretched to form long wires. Chemists classify all the elements that lie on the left of the staircase in the line on the periodic table as metals, meaning these here. The elements to the right of this line are nonmetals, as shown here. So a metal is a malleable and ductile element that has luster. It has a good heat and electrical conductivity, and it tends to form positive ions. Nonmetal is an element that is not flexible, it does not conduct electricity, and does not form negative ions. So metals tend to form positively charged ions, or cations, where nonmetals tend to form negatively charged ions, or anions. So if you are handling a piece of aluminum, you are holding a collection of positive ions. If the aluminum ions are positively charged, then why do these ions stay together? Shouldn't they repel each other? The answer to these questions are explained in this example problem. So, the following process for sketching the atomic structure illustrate how atoms of aluminum bond together to form a solid piece of aluminum metal. So, for our solution, step 1, we need to draw the Lewis dot diagram of the atom, which in this case is aluminum. Aluminum has 3 valence electrons, meaning I have 3 dots around my aluminum symbol. Then we need to determine how the atom can fill its outer energy level. An aluminum atom can obtain a full outer energy level by either gaining 5 electrons or losing 3 electrons. It is much easier to lose 3 electrons than it is to gain 5. So an aluminum atom will tend to lose 3 electrons to become a stable aluminum ion, as shown here. Now, step 3, we need to make a bond with the aluminum ions. Well, as I put them closer together, they're going to repel each other since they both have positive charges. Now, 2 aluminum ions are both positive ions, so why would they stick together if they naturally repel each other? Well, the key to this is the answer is that both atoms lost electrons to become ions. So, aluminum ions are attracted to the free-moving electrons which are in between them. So you can think of a strip of aluminum metal as aluminum ions remaining together because of their mutual attraction to the free-moving electrons. As you can see here, there is this sea of free-moving electrons. Now note that there is an equal number of protons and electrons in this system. So even though the electrons are free-moving, overall, each atom is still neutral. Ionic compounds. A rock salt is a compound called sodium chloride. It is made up of the elements sodium and chlorine. Since sodium is a metal and chlorine is a nonmetal, the resulting compound is called an ionic compound. The ions in the sodium chloride are held together by a force of attraction between the positive sodium ions and the negative chloride ions, and this is called an ionic bond. This example problem will show you how to apply the process to produce a sketch of the atomic structure of sodium chloride. This example will allow us to shed light on why sodium chloride forms rectangular crystals. So a compound is a pure substance formed from atoms of two or more elements with the different atoms joined in fixed ratios. Ionic compounds is a pure substance formed from a metal and a non-metal. And an ionic bond is a bond formed by the simultaneous attraction between positive and negative ions. As we can see here, there's a lattice structure that is produced because we have negatives joining to positives. So, our example problem here says to sketch a diagram illustrating how the atoms of sodium and chlorine form ions and bond together to make sodium chloride, a common crystalline compound. So step 1, we need to draw the Lewis dot diagrams for each atom. Step 2, which we've done here. Step 2, we need to determine how each atom can obtain a full outer electron level. Well, sodium can obtain an full outer energy level by either gaining 7 electrons or losing 1 electron. Metals tend to have weaker attractions for their valence electrons. Therefore, they tend to lose electrons. So sodium atom would tend to lose the 1 electron to become a stable sodium ion. A chlorine atom can obtain a full outer energy level by either gaining 1 electron or losing 7 electrons. So the nonmetals tend to have a greater attraction for valence electrons. Therefore, they tend to gain electrons. So a chlorine atom will tend to gain 1 electron to become a stable chloride ion. Step 3, we need to make a bond with the positive and negative ions. This ionic bond is represented by a line segment between the two ions. Positively charged ions are attracted to negatively charged ions and vice versa. This attraction holds the substances together to form a sodium chloride crystal. The crystal is shown here, where we have our positive ends and our negative ends, and they are joined together. Each ionic crystal results from the neutral attraction of positive and negative ions. Covalent bonds. So although you will look at plastics in much greater detail in Chapter 3 of this unit, for now, the essential idea is that plastics are primarily made up of carbon and hydrogen atoms. Since both carbon and hydrogen are nonmetals, the resulting combination is called a molecular compound. Molecular compounds do not involve ions, so the carbon and hydrogen atoms are held together because the nucleus of a carbon atom is simultaneously attracted to the same electrons as the nucleus of the hydrogen atom. This simultaneous attraction is called a covalent bond. The resulting combination of carbon and hydrogen atoms is called a molecule. So a molecular compound is a pure substance formed from nonmetals. A covalent bond is a bond formed by the simultaneous attraction of two nuclei for a shared pair of electrons. And a molecule is a particle containing a fixed number of covalently bonded nonmetal atoms. The basis for sketching a diagram of a model consisting of carbon and hydrogen atoms is illustrated in this example problem, but we will learn this more in detail in Chapter 3. So our example problem. Sketch a diagram illustrating how atoms of carbon and hydrogen bond together to form a long chain-like molecule. So step 1, we need to draw the Lewis dot diagrams for each atom. Carbon having 4 valence electrons and hydrogen having 1. Step 2, we need to determine how the atoms can obtain a full outer energy level. Carbon atom can obtain a full outer energy level by either gaining 4 electrons or by losing 4 electrons. In cases like this, an atom will often share electrons. And a hydrogen atom can obtain a full outer energy level by either gaining 1 electron or losing 1 electron, and in this case, the atom will often share electrons. Step 3, we need to make the bonds with the 2 non-metal atoms. Non-metal atoms, like carbon and hydrogen, tend to require electrons to fill their outer energy levels. When this situation occurs, both atoms share electrons to form a covalent bond. So in this diagram, the carbon atom still does not have a full outer energy level. So it will either bond with more hydrogen atoms or with more carbon atoms. So here, this carbon has a complete outer energy level. And this carbon can join to either another carbon or another hydrogen atom. A plastic strip is made up of long strands of carbon atoms sharing electrons with one another, and with hydrogen atoms, each long strand as a molecule. So this just keeps going and going. This line segment represents the covalent bond formed by 2 atoms sharing a pair of electrons. Adjacent strands will have a slight attraction to each other, forming a piece of plastic. So it is this slight attraction which keeps all the plastic molecules aligned. So earlier, we sketched diagrams of the atomic structure of commonly found categories of matter: an ionic compound, a molecular compound, and a metal. So we talked about rock salt. Atoms that make up this substance is sodium and chloride. And the category of this matter is an ionic compound, with its properties of being brittle, having a high melting point, and being soluble in water. Hard plastic, on the other hand, is made up of carbon and hydrogen. The category of matter is a molecular compound, because it's both 2 non-metals. It is also flexible, has a high melting point, it is insoluble in water, and does not conduct electricity. Aluminum foil, on the other hand, atoms that make it up are just aluminum atoms. It is a metallic element, and it is malleable, has a high melting point, it is insoluble in water, and a good conductor of heat and electricity. So, categories of matter. Everything we see and interact with is comprised of substances that are made from atoms. If you want to understand the properties of substances, a good place to begin is by identifying the category of matter. The next step is to link the diagrams of the atomic structures you sketched for the category of matter to the properties of these materials. So, breaking bonds. To make a specific material, you need to create a specific combination of atoms. To create a specific combination of atoms, we need to do the following. 1, we need to find a natural source of the atoms you want. These atoms are most likely will be bonded in a way that is different from the way that you want. Secondly, we need to break the existing bonds between the atoms in the natural source to separate them. Step 3, we need to create new bonds between the atoms required to form our product. Assuming you have a natural source of the atoms you require, how can the existing chemical bonds between the atoms be broken? For many substances, it is just a matter of adding water. So, observing chemical change. You can tell a chemical change is occurring if a new substance is produced, accompanied by a change in color, odor, state, or energy. Changes in state usually involve the formation of a gas or a solid. Changes in energy may be exothermic, where energy is released, or endothermic, where energy is absorbed. Chemical changes indicate the bonds between atoms in the original substances have been broken, and the bonds have been formed to create new substances. In the next activity, we will observe chemical change. So chemical change is a change in which one or more new substances with different properties are formed. An exothermic change is a chemical change in which energy, usually in the form of heat, is released into the surroundings. And an endothermic change is a chemical change in which energy is absorbed by our surroundings. A solution is a mixture made up of more than one type of particle. When the particles intermingle with one another, solutions appear as though they are composed of only one substance, even though they contain more than one species within them. Many of the reactions that occur in the world occur when a matter is dissolved in water, forming an aqueous solution. So a solution is a homogeneous mixture of dissolved substances that contains a solute and a solvent. Then an aqueous solution is a solution in which water is the solvent. Now keep in mind that homogeneous means that you cannot tell between the two different parts that are dissolved within that solution. So, why does salt solution shown in this figure appear transparent? Where have the particles of the ionic crystal gone? The particles of the ionic crystal have dispersed throughout the water, and the ionic compound has dissolved. But why does it appear to break apart? When something becomes dissolved, its bonds have been broken down in some way, and as a bond breaks, the particles separate, and they are free to move as individuals throughout the solution. These particles can be either molecules or ions. The substance that is broken down is called the solute, and the substance that breaks the bonds of the solute is called the solvent. Remember, a solute dissolves in a solvent. Solute is a smaller word, which means, or one way to keep this in mind is that the solute will be in the lower quantity than the solvent. So a solute is a substance in a solution whose bonds are broken by a solvent, a substance that dissolves. A solvent is a substance in a solution that breaks down the bond of a solute, a substance that does the dissolving and is in the greater proportion in the mixture. So, a solute and solvent. Using a solvent like water is an excellent way to break down certain types of bonds in a substance. For this reason, many reactions naturally occur in solution. When a solute has been broken down into its individual parts, these parts are no longer bonded to other ions. This allows each ion to collide with and form new bonds with substances introduced in the solution. So in this activity that they are talking about, we purposely break bonds between cobalt-2 ions and nitrate ions, and the bonds between the sodium ions and carbonate ions with the addition of water, which is activated as a solvent. Once the old bonds are broken, the particles are free to collide and form new bonds, some of which resulted in a formation of a precipitate. So the particles of the solvent are used to break apart the bonds in the solute. So here we can see we have an ionic crystal. We add the solution, which breaks them apart. Okay. We have another ionic crystal, adding water, breaks apart the ions, and when we combine the two, some of them will still stay in solution, but some of them will precipitate out and form a precipitate because they are much stronger bonded together, forming a solid. So, water is a very important solvent. It has the ability to dissolve most ionic crystals because they are made up of positively and negatively charged ions. Some ionic compounds have lower solubility in water than others, but all ionic compounds dissolve in water to some extent. Some substances are held together by covalent bonds, like oil, do not dissolve in water, but others, like glucose, readily dissolve in water. So could dissolving a molecular compound in water be related to the compound's charge? As described earlier, in some covalent bonds, electrons are not shared equally, and the molecule ends up with an uneven charge distribution, just like water. Water molecules are electrostatically attracted to these molecules, and water molecules will surround the slightly charged particle and cause it to dissolve. Some molecules, however, will not have areas with different charges, and as a result, they do not interact with the water molecules and therefore will not dissolve in water. This is a picture of an ionic compound being broken apart by water. So as we add the water, okay, it pulls the anion and the cation apart. As the cation is pulled apart as a positive charge, and the oxygen part of the water molecule surrounds it, where when we have our anion here, it is the hydrogen part of the water molecule that surrounds it, allowing it to stay in solution. So molecular compounds that do not dissolve in water. So triglyceride is a fat molecule, and as we add it to water, they don't interact because there's no area here with a charge, okay? It's all evenly covered by hydrogen. And I just thought this was a cute little comic here. So did you ever wonder why many industrial factories are located by a source of water? The simple answer is the plant process often require large amounts of water for chemical reactions that occur within the plant. Water is a major requirement for most chemical industries because it effectively breaks the bonds and allows the chemical reaction to occur. When an ionic compound dissolved in water, the bonds between the ions within the ionic solid are broken by water molecules. As a result, the free ions exist in water, and the breaking down of the ionic compound into its smaller parts is called dissociation. So notice when an ionic compounds dissociate, they produce negatively charged and positively charged particles within the solution. If you have a negatively charged and positively charged particles within a solution, the particles can move in response to other charged objects. A simple conductivity test involving placing two electrodes in a conductivity apparatus in a solution. The different charges of each electrode attract different ions. If the ions are dissociated and free to move, they can move towards one of the electrodes, and the resulting movement of ions acts to move charged particles, completing the electrical circuit of the conductivity meter. Solutes that conduct electricity or an electrical current when in a solution are called electrolytes. So dissociation is the separation of an ionic compound into individual ions in a solution, and an electrolyte is a solution that forms, a solute that forms a solution that conducts electricity. So here's our conductivity meter. Okay, it is within an electrolytic solution. In this case, it is just salt and water. And we put in our electrodes, we've got a battery and the light bulb will light up. And this is because the dissociated ions can move towards the oppositely charged electrodes of the conductivity meter, and this movement of ions or charges completes the circuit of the conductivity meter. So non-electrolytes. Water cannot break down the covalent bonds between the atoms of molecular compounds, yet many dissolve in water. Molecular compounds do not dissociate like ionic compounds, and water simply separates the molecule of the solute if they have an uneven distribution of charge, due to the unequal sharing of electrons in the covalent bonds. So if we do the same test with a non-electrolyte, there will be no lighting up of their bulb. So the dissolving equation of a molecular compound. We've got a solid molecular compound, here it's sugar, okay? Or add water, and now it's just become aqueous, that's the only difference. So a solution of molecular compounds does not contain a negative and positive ions because of the lack of oppositely charged particles in solution. The electrical circuit of the conductivity apparatus will not be completed, and a substance that forms a non-conducting solution is called a non-electrolyte. So a non-electrolyte is a solute in solution that does not conduct an electrical current. In this case, it will be a molecular compound. And that's it for today. Thank you very much, and we'll see you tomorrow.